Yeah, we need to do similar thing with let's say you train for equivalent, then let's say
It seemed like a gold line. Yeah. Through a hole. Just one here. I couldn't see from the back. Oh. And the door like came on. Who's this guy? Gone. Oh, no, sorry. I was who's this guy? No, it's because I can't see from the back. Fair enough. Yeah, I'm Nico. James. James, okay. Where are you from? Yeah, well, cool. And yourself?
There was a lobby area.
Oh, thanks. Well, otherwise I write too small. The bigger the chalk, the bigger my handwriting.
I'll bring up some railroad chalk.
Yeah.
We have a, okay, I'll just do that one now. Yeah, okay. When it looks like it's time to start.
Okay. Anyone else wandering in? Okay, let's get started. So I'm Mathew Schwartz. My lectures are about collider physics and QCD. I'm going to talk mostly about collider physics. Just give you kind of an overview of kind of things you should know about how to think about the Standard Model and to some extent beyond the Standard Model in the context of the Large Hadron Collider. And depending on time, I'll do some more aspects of quantum chromodynamics and understand how you can connect it to things you measure. And this interplay between perturbative calculations, non-perturbative physics, and experiment is very important and very subtle, and I'll try to elaborate on a few of the ideas. So basically an outline, the kind of topics I'm going to cover are, well, collider physics. So this means a lot of different things, but mostly it's about the kinds of things we can measure at a Hadron Collider, what they tell us, how we calculate them, and so on. I'll talk a little bit about particles in the Standard Model. So this is a subject which is important to know, but doesn't seem to be kind of covered in a uniform way anywhere. So things like, what does a top quark decay to? What does a tauon look like in an experiment? These kind of things which you should know, but often kind of get glossed over. And maybe if you take a particle physics course, you get it, but often it's not reviewed at the level after you know quantum field theory. So I'll try to connect some of these topics. I'll talk about quantum chromodynamics. And I won't be doing the NNLO calculations in QCD. Maybe Sally will do one for the Higgs process. But mostly I will try to give you some intuition for some aspects of QCD that you may not be familiar with, and try to just give you a feeling for how the theory works. And one thing I want to do is connect QCD to collider physics. And that means understanding certain aspects of factorization. So why we can describe collisions through Parton distribution functions and some perturbative process. What are the corrections to that? How well we understand these features. So I'll try to emphasize those to the extent I can in the time we have. I'll also talk about the Proton model. So the Proton model largely exists independently of quantum chromodynamics. Proton model is the assumption that the proton is made up of a bunch of essentially freely interacting loose quarks and gluons with probabilistic distributions. And this is what we assume and we use to calculate everything at colliders. And there's an extent to which that can be justified by quantum chromodynamics, and I'll talk about the connection between these two things. But this is actually a very predictive model, which explains a lot of the phenomenology that we see. And then if there's time, I'll also talk a little bit about jet physics, which is a subject dear to my heart that I work on. And there's a lot of interesting developments in jet physics in recent years. So I don't think I'll be able to cover all of this, but we'll see where they go. And if you have opinions about what you'd like me to cover more than other topics, please let me know, and I can adjust accordingly. So I'm gonna use this board, and well, I should have probably started with the one down here. But I'll use this board, and I'll try to show some slides occasionally. I'm not gonna give PowerPoint lectures. Won't be any equations, but I'll show pictures like this picture of the LHC tunnel, just to give you a little perspective. There's things that I just, it's better to plot than to sketch. Maybe I'll give you some references. So there's a great book on collider physics called QCD and Collider Physics by Ellis, Sterling, and Weber. This is really a classic book. It has a pink cover, so people often call it the pink book. It describes a lot of the connections between QCD and colliders. Some of the stuff is a little outdated, but it's a great reference and gives more detail than I will about a lot of topics. More recent stuff, there's some lecture notes that you can get online. There's notes by Tao Han, which I like, which is HEP PH 0508097. I don't know if you can read that, but that's what it is. And also Peter Scans has some nice notes that I like, which is 11042863. And another reference is a book called Quantum Field Theory and the Standard Model, which I wrote, which covers a lot of the QCD stuff. So I hope to write lecture notes for the stuff I'm talking about, and mostly it'll focus on this collider physics stuff, which isn't covered in standard textbook treatments. Okay. So I want to get started. Actually, before I get started, I want to get a better sense of who these people are in the audience. So I just want to show of hands of what you're interested in, what you work on. So choices, things are like standard model physics, beyond the standard model, dark matter, formal theory, and so on. So who in the audience is working mostly on standard model physics? Just raise your hand up high. I think it might be useful for the rest of you to see this. So a handful, maybe 5 or 6. Dark matter? Okay. So that's about half, maybe. BSM model building? That's maybe overlapping half. Formal theory? 1, 2. Other topics? What's another topic? Cosmology. Who's doing cosmology? Okay. Other topic? Lattice? How many lattice people do we have? 3 or 4 lattice people. Okay. Okay, so it's a good mix. Mostly, I think, BSM focused, but there's still a smattering of people interested in standard model. So the standard model people, maybe some of this will be more review than to the BSM folks, but I'll try to give an overview of stuff that's relevant to everyone. So a lot of what we're talking about is related to this machine. So this is the tunnel for the Large Hadron Collider. It's this 27-kilometer tunnel going near Geneva, which is up there, and it goes on between the France and Switzerland border. It's really an enormous enterprise that collides protons, currently at 13 TeV. It's running very actively, and it's actually been taking data for the last couple of months, and it's already accumulated almost 4 inverse femtobarns, which is great. So we hope to have some actually good results coming out by ICHEP in early August. So to start thinking about the LHC, we need to start thinking about units and get some sense of what the design specifications were for this machine. And to do that, we just need to get some numbers. So what are the units of cross-section do we usually use? Femtobarn, picobarns. So what's a barn? Do we know what a barn is? What? 10 to the minus 24 square centimeters, 20 to the minus 28 square meters. So let me figure out how to do this in the right order. Let me start with this one. Okay. So one barn is 10 to the minus 28 square meters, or minus 10 to the 24 square centimeters. How big is a proton? Anyone know? About a Fermi. How big is a Fermi? 10 to the minus 15. So you might say the radius of the proton is around 1 femtometer, 1 Fermi, which is 10 to the minus 15 meters. Okay. How do you know this? GeV. Yeah. So So it's close to a GeV scale. There's a nice conversion, which is how I remember this, which is lambda QCD, the strong interaction scale of QCD, which is around 200 MeV, is 1 inverse femtometer, which is roughly the size of a proton. So it's a typical strong interaction size of a nucleus. Does anyone know why this is called a barn, where this unit comes from? What? Where you raise kale? What? What's like hitting inside of a barn?
Like getting something with that cross section.
Is
A large cross section.
it's a large cross that has about 28 square meters? It's from the 30s. That's right. It's from the original nuclear physics. So actually, nuclear reactors, right? So Enrico Fermi came up with this, and it's because he was trying to make controlled nuclear fission in his reactor in Chicago, and he would find that the neutrons kept hitting the other uranium. He's trying to make some kind of stable, controlled system, but they would decay and they would produce all these fission products, and he couldn't keep the neutrons from hitting the other uranium molecules. So he said it's like hitting a uranium molecule is like hitting the broadside of a barn. And so we have the cross section, which is really the cross section for neutron uranium 235 scattering, is around 1 barn. And it's useful to remember this, right? So this means you think of the uranium as a big ball, right, with all these little nucleons in it, 235 of them. So you can use this to figure out what's the cross section for proton-proton scattering. Right? So it's roughly a Vault or a barn, but obviously a proton is much smaller than a uranium atom. Let's see. So if the radius in units of the proton goes like 235 nucleons to the third, then the area, let me say, sigma goes like r squared, which is 235 to the 2/3. So the sigma for proton-proton scattering should go like 235 to the minus 2/3 barns. So what's 235 to the minus 2/3? Well, it's smaller by some factor that's around 2/3 of this, so you can work it out, and it's around 30 millibarns. Right, so it's something smaller than a barn. It's a Vault or millibarns. You can also do this. So the radius of the proton, if I calculate the cross section, that's the classical cross-sectional area, pi r squared, so that's roughly 3 times 10 to the minus 30 square meters, which is also 30 millibarns. So this is roughly the characteristic size that we're interested in, right? The size of a proton. So protons scatter each other. They see something with a cross-sectional area of around 30 millibarns, right? This is what we have to work with. So when you collide, the LHC collides this, and that tells you roughly how often you have collisions and how often protons scatter off each other. I mean, I should say this going between this classical idea that there's some hard thing with a cross-sectional area and the quantum mechanical notion of a cross-section. The thing we call cross-sections quantum mechanically reduces to this classical notion in the limit that you can treat it classically, but it's a more general concept that we calculate with Lyman diagrams. And I assume all of you have kind of seen what quantum mechanical cross-sections are in your field theory courses, but it's useful just to do some kind of simple dimensional analysis to make sure that it's consistent with our intuition. Okay, so we're not interested in just seeing how big a proton is. We're interested in seeing the cross-section for something like producing some particles of interest at the LHC. So what's the cross-section for something like W boson production? How'd you figure that out? Electroweak scale, good. So pp to W. Can you give me a guess? What's the electroweak scale? Picobarn. Where do you get picobarn from? Well, if you know it, you know it. But if you don't know it, what do you know? 90 GeV. Okay, you know the mass of the W. So you say 90 GeV squared, right? Because what else are you going to guess, right? It's the mass of the W. Well, it's not really the mass of the W. Maybe 80 GeV. But it's roughly G Fermi, right? Which is the strength of weak interactions. W mediates radioactive decay with Fermi constant, right? So what is this? Well, this is, here we had basically 100 MeV gave us a millibarn. So 100 GeV squared is going to give us a factor of 10 to the minus 6 times what we get for a cross-section. So we get 10 to the minus 6 millibarns, or 1 picobarn. So this is just the characteristic size of scattering, electroweak scattering at the LHC is this picobarn cross-section, which means that we have to collide 1 million protons together to produce a W boson, right? 1 million may seem like a lot, but it's not a lot on the LHC scales. We're colliding billions and billions of protons every second. What about Higgs boson production? What's that cross-section? Anyone know? Femtobarns. How do you get that? What? I'm sorry. This is not. I got this unit wrong. This is a nanobarn. Right. And femtobarn. Well, femtobarn you can know. So how much luminosity has the LHC accumulated so far? 25 inverse femtobarns, right? So if the Higgs cross-section were a femtobarn, it would mean we've only produced 25 Higgses, right? So it better be bigger than a femtobarn, right? But roughly, so how do you produce this? So the dominant production channel is this top loop gluon fusion channel, right? So it's produced through a loop. And so basically you get this loop factor of roughly 1 over 16 pi squared times something like a weak scale cross-section, right? So this factor is roughly 10 to the minus 3. So you get another factor of 10 to the minus 3, or you get 10 to the minus 9 millibarns, which is around a picobarn.
It's for gluons being less luminous.
Why do you say gluons are less luminous than quarks? So we'll get into that a bit. But to leading order, everything's the same when you're at high energy, and it's just this big soup, this big mess of stuff. And there's some relative proportions, but it's order 1, right? And we're talking about factors of order 10 to the 3 here. So we'll talk about these luminosity functions and some kind of intuition you can build for them. What's more important is that all of them die off at high energy. So it's much less likely to produce something at high energy than low energy, and there's some slightly larger rate to produce, have gluon-initiated production or quark-initiated production, but it's order 1, maybe a factor of 10 or so on.
You were about to loop with the square of the loop factor, right?
Yeah, well, this is squared. The pi squared comes from the square of the loop factor. You get something like 4 pi from the loop. I mean, it's just rough, but this is basically where it comes from. You get this extra suppression of some numerical value, and you get these tops, which are order 1, and the couplings of order 1, so you don't get any extra coupling suppression. Just roughly, that's how I think about it. And of course, you have to do the actual calculation. Really, it's closer to 40 picobarns, the inclusive cross-section. And it depends on the energy. The cross-section goes up from, when you go from 8 to 13 TeV, it goes up by about a factor of 4. So there's order 1 factors here. But roughly, this is what we're looking at. We're looking at, to produce Higgs bosons, we need to collide a billion protons together to produce each Higgs boson. Right? Okay, so given that, how many protons do we have to collide to actually observe? What kind of design specifications do we need to produce, to find the Higgs boson? So how do we actually see a Higgs boson? What's the kind of how was the Higgs boson discovered? What? Gamma gamma. Okay, what's the branching ratio of Higgs to gamma gamma? 10 to the minus 1? 10 to the minus 4? What? Minus 7. We got minus 1, minus 4, minus 7. Sally, what's the branching ratio of Higgs to gamma? 10 to the minus 3. Okay. So the branching ratio. I guess we're going to cover this in Sally's lecture. At least she knows the answer. Okay. Right. Okay. So this was, we needed to collide a billion protons to get a Higgs. Now we need to collide a trillion protons to get a Higgs to gamma gamma. Say we want something like, say we want to see 100 Higgs in a year. It's a kind of reasonable goal for a measurement. Maybe there's a factor of 10 to the minus 2, some kind of efficiency, detector efficiency. I mean, I don't know how to guess these efficiency factors. So we need, let me see, I work this out. We need, how many, so a year is 10 to the 7 seconds. So we were supposed to get, how do I want to write this? So we had, we needed 10 to the 9 Higgs times 10 to the minus 3 times 10 to the minus 2 divided by what am I trying to do here? Times 10 to the minus 2 efficiency, 10 to the minus 2 Higgses. So we get 10 to the minus 7, and then we have 10 to the 7 seconds in a year. So this leads to around, we need 10 to the 9 Higgses per second. So we need 10 to the 9, we need about 1 billion Higgses per second in order to get 100 Higgs to gamma gamma in a year. Right? So this is kind of a reasonable goal for what we should think the LHC should be able to do. Right? It should be able to produce something like 10 to the 9 10 to the 9 protons. Proton collisions per second. Right? So we want 10 to the 9 scattering of protons to scatter off each other every second in order to produce this kind of cross-section. Right? So it would have been 10 to the 9 protons to produce each Higgs, but then because of these efficiency factors, we need to produce about that amount of collisions a second, right? Including for things like we don't run all the time, and that's all included in this efficiency factor. So that just gives you a rough idea of what we need the LHC to do. So this is 10 to the 9 is 1 billion, so this is 1 gigahertz. So 1 billion collisions per second was what our goal is. So how does the LHC achieve this? Well, you can see there it's a big ring. And the way the LHC works is you have protons going around one way and protons going around the other way, but they're not continuous. We don't have continuous streams of protons. They're collected in little bunches, right? If they were continuous, you wouldn't be able to tell one collision from the next. You also wouldn't get the accelerator to work. So the way it actually works is you have this ring, and you have these little bunches, and you try to put as many protons in the bunch as you want. And a bunch might have around 10 to the 11 protons. That's kind of a typical fill size on the current running of the LHC. Then there's a spacing between the bunches. At the previous run, they were separated by 50 nanoseconds, and now the current run, they're 25 nanoseconds. Clearly, the closer you put them together, the higher luminosity you can achieve. So there's around a 25 nanosecond spacing. So 25 nanoseconds, so 1 over 25 nanoseconds is, so nano, I forget what nano is. Nano is 10 to the minus 9, so this is 10 to the 9, so it's 40 gigahertz, 40 megahertz. It's 1/4. Yeah, you divide by, so it's gigahertz divided by 25, which is 40 megahertz. Right? So that means that basically every 40 megahertz is the rate for collisions of the bunches against the next bunch. And what we're going for is around, so in order to get from 40 megahertz to 1 gigahertz, we need to have about 100 proton collisions for each bunch crossing. Right? So we want Okay, so how do we do that? Well, what we have to do is to squeeze the bunches down. And the smaller we can squeeze them, the more likely the protons are to collide within the bunches. Right? So the number of collisions will be the number of protons per bunch squared, because we have two bunches, so this is 10 to the 11 squared. And then we need to weigh the cross-section. So we know the proton cross-section. So proton-proton cross-section, which is around let's say 10 millibarns. And we have to divide that by the cross-sectional area of the bunch itself. Right, obviously, the bunch is very wide. The protons are going to collide, so the smaller we get it, so the beam. So what does this look like? Well, it depends how much you squeeze them. So I think at beach cross-sections, they could squeeze them to around 10 microns, which is around 10 to the minus 5 meters. So this gives me around 10 to the minus 10 square meters. 10 millibarns, we said was 10 to the 31. 10 to the minus. 10 to the minus, what is it? 10 to the minus 30? 10 to the minus 30. Okay. So this 10 to the minus 10 squared. So we have 10 to the minus 30 divided by 10 to the minus 20 is 10 to the minus 10. And here we have 10 to the 11 squared. Just not squared? That's right, 10 to the minus 5 squared. Okay, so we have 10 to the minus 20, 10 to the 22. So we ended up with 100. Which is what we wanted, right? So the point is just that the design of the LHC is kind of what we want to produce Higgs's for Higgs discovery. And these were the design specifications that we built the thing. And of course, now that we're trying to go beyond the Higgs and see more exotic signals, we can go higher than that, for example, by putting more protons in the bunch, colliding them more often, more generally increasing the luminosity, increasing the fills. So putting more protons in the bunch is one of the best ways to increase luminosity, having it run more and keep the beam stable for longer, and so on. So right now the LHC is able to see picobarn cross sections because we've gotten 25 inverse femtobarns, so you can work out the numbers and you should see thousands of Higgses in that time. We don't see them all, but they're produced, and you put some branching ratios to see them. But if we want to see femtobarn or sub-femtobarn, attobarn cross sections, we're going to need to accumulate an attobarn, an inverse attobarn of data, which is a design goal for future upgrades of the LHC. The hope is that this run will get to maybe 30 inverse femtobarns, and then in future runs we'll get to around 100 a year before the next upgrade.
How can you tell the difference between in the one bunch? So there are 10 to the 11 protons,
Yeah.
and they collide together, and there will be a lot of product out of it. How
Right.
can you tell the difference between?
That's a great question. So what we said is that each time you collide a proton, you get around 100 scattering events, right? So this is this is called mu. It's the number of roughly inelastic proton scattering. But out of those inelastic scatterings, only 1 in a million does something interesting, right? So most of them are what's called minimum bias, where you just scatter. So I like to think of the proton as a big soup. It's just this kind of mess of liquid and so on, and sometimes something hard will collide. And when it's hard, you see a big explosion, but mostly you see crap. And mostly that crap just goes down the beam line. It's just soft stuff that you don't see at all. But you can resolve, to some extent, you can resolve some of the details of these 100. You can't see them all, but you can see, because the proton, this is going at the speed of light. So actually, the proton doesn't really look like a beam. Well, it really looks like a pancake. It's kind of spread out by Lorentz contraction. But it's also displaced. So when you collide, I don't know how to draw this. So it's really a bunch of protons, a bunch of things here, a bunch of protons there. And they collide, and someone would collide here, and one would collide here, and one would collide there. So you can see this longitudinal displacement of where they collide from the tracks. And so part of the design specification of the LHC is to have a tracker that's good enough to resolve the different interactions. So you can see what comes from what's called the primary interaction, which is the 1 in a million that produces a hard interaction, and the rest of them are almost all minimum bias, which you don't care about. And it's helpful to be able to distinguish it so you can tell which particles came from that.
But how can you tell the difference between the primary vertex versus the secondary vertex?
Well, primary is the one that produces the hard stuff.
I see.
Yeah, and the secondary vertex often means something else. So it's not primary or secondary. Secondary is from the primary when you have a decay of something like a B. So we'll use that language to talk about pile-up interactions, which are these other kind of soft things. So you can see them, and maybe I'll show I don't think I have one here, but for the next lecture I'll show you a plot of what that looks like. So, how's the LHC doing? So here's a plot of the instantaneous luminosity per day. So I just got this morning. This is the runs in 2016. You can see early on they got some luminosity, but for the last week or so, they've been actually getting sustained luminosity. So what are the units here? This is hertz per nanobarn. So what the heck is a hertz per nanobarn? This is great because they used to write it in inverse centimeter squared per second, and then they started going to hertz per nanobarn, which you may say both of these units are horrible, but they're not so bad. So what is a hertz per nanobarn? So what do we do? We're talking about around 10 hertz per nanobarn. So the number of collisions is this luminosity times the cross section, which is around. So we said the cross section is 10 to the minus 30. Well, let me write it all in terms of meters squared. So this is the number of events is the luminosity times the cross section, and so the cross section is so nanobarn is 10 to the nanobarn is 10 to the minus 9 times 10 to the minus 28. So we get 10 to the minus 2 times the minus so this is 10 times 10 to the 7 or 10 to the 8 hertz. Right? So that's 10 to the 8 hertz is 0.1 gigahertz. Right? So that's about 100 million collisions per second, which is similar to what we're looking at here, which was this kind of gigahertz goal. Right? So we're not quite there. We're at about a tenth of a gigahertz. This rate sometimes, so this, you could also write this in terms of centimeters per second, and I think it's 10 to the 34 inverse centimeters squared per second. That's another unit you'll see for instantaneous luminosity, which is kind of a design goal. So, I mean, this is about what the LHC is capable of doing currently. The hope is to maybe get another factor of 10, or at least, 2 out of luminosity, but it's running pretty well. And so it's able to accumulate, well, we can show you a different plot. So here's the integrated luminosity of the LHC as a function of time. And again, these are, days here. So it's accumulating very fast. And you can see over the last, this is about, so a week is up to here, maybe a week and a half. It's been really accumulating almost linearly a lot of data. So now we have 3 inverse picobars of data as of this morning. It's currently not running, but it's going to start up again pretty soon. And it'll keep taking data. So this is great. This is doing better than was expected a couple of weeks ago. There was a shutdown here, which I think was due to a problem with the proton synchrotron that they had to fix, and so on. But it's it's fun to see that this thing is actually running, and you can look. There's web pages that actually show this live. So here's, if you go, well, I can put a link to this on the wiki, but this is something that's fun to look at. It just shows the current operation. So this is the past 24 hours of LHC operation, and these plots show the luminosity of the 2 beams, so that's red and blue, and then the energy. So you see the energy, when they get it up, it runs at about 6.5 TeV per beam, and the luminosity slowly goes down. Why does the luminosity go down with time? What? Because the weasel, no. Then it goes down very sharply. Energy loss? What? Loss of beam focus? What? Solar powered. It's an interesting idea. No, I mean, the LHC takes about as much energy as the city of Geneva to run. I don't think you can run that with solar power. No, I mean, it's the beam loss. Yeah, I mean, you're colliding protons, right? So you're colliding them, a billion times a second, you're going to lose protons from those collisions, right? It adds up. And it adds up over time, right? A billion this second, a billion that second, you add them up, and you start losing some beam. And so the LHC has these fills. They run a fill here, and they try to keep as much beam as they can, and then at some point they stop, or something goes wrong, and they have to dump the beam, and then they do it again, right? So they have these runs, which run for about half a day, and then they'll fill it up again as soon as possible.
What's the blue and yellow stuff in the previous slide?
Blue and yellow stuff. I have to go back to PowerPoint. Here?
Yeah.
Yeah, so this is what's delivered and what's recorded. So the machine, this is for CMS. There's a similar one for Atlas. So the beam, there's the accelerator, which runs the beams, and then there's the people doing the experiments. And they have to have their experiment running and taking data and colliding the protons and measuring them. And they don't always do that, right? I mean, you can see, so the yellow is how much they actually recorded, and the LHC is how much it delivered, right? So the accelerator says, we're going to give you this, you can take it or leave it. And sometimes they take it, most of the time they take it, but sometimes they don't, they're not recording. You know, something's not working on the experiment, and so they don't take data. But most of the time they take it, and this is actually a very good efficiency for running. But there's a lot of things that help degrade the amount of data actually recorded. Yeah? What's offline?
See the previous materials.
Oh. Offline luminosity. I don't know what that means.
Offline luminosity that they predict, and then they have a separate measure for online luminosity, which is actual luminosity.
Okay, so the offline is their prediction, and then they measure it. This isn't exactly what they measure, but I'm not exactly sure. But that sounds reasonable to me. And I'm sorry, I should be repeating your question so it's recorded, and I haven't been. So I'll try to do that. Remind me if I don't. Okay, so where were we? So we have 100 inelastic collisions per second, and we have around, where were we, a gigahertz of collisions. So a gigahertz, I'm sorry, we have 100 collisions per beam crossing, right, which leads to 1 billion collisions per second, right, because the beams cross every 25 nanoseconds. Most of the loss? Yeah. Right, just when the protons bang into each other and breaking apart, right? So that's most of them, right? The ones that are inelastic cross sections anytime a proton breaks apart. There's also elastic proton scattering, which is a very small fraction of it. And there's other interesting aspects of elastic scattering, like diffractive scattering, which some people are interested in. But mostly protons scatter across each other and they break apart, but they don't produce a hard interaction, with tens of GeV. Most of the interactions are GeV scale, weakly inelastic scattering, where it just breaks apart and produces some mess, and things fly in every direction, mostly down the beam, and so that's not interesting. And so that's, you could see only 10 to the only 1 in a million proton collisions produces a W boson, which is a rough measure of the kinds of things you're interested in. So that means that 999,999 times the protons collide, you don't get anything of interest, right?
It's like 10% of the beam is lost.
This one? So you want to figure out how to calculate this? Well, we could try.
Get a sense of like where most of the loss.
Yeah. So we had 10 to the, what do we have here? We have 10 to the 11 protons per bunch, right? And every second we lose 100 of them. That's a really tiny fraction, and then we have, yeah. So we might get a value factor of 10 to the 3 or something, yeah. Right.
Or maybe it's a faster accumulation in terms of the time scale.
Yeah, but right. There's other things. The protons lose. They also interact with gas in the beam. They scatter, and they lose them as they go around. So there's just many causes of protons colliding with things that causes them to degrade. But okay, right. So what do we get? So we have 1 billion collisions per second. So gigahertz. So you might be more familiar from this gigahertz scale from like your computer, right? They also run at the gigahertz scale. So that gigahertz is the speed of the processor, right? So it does about 1 billion processing steps per second, right? But this is a problem because we have 1 billion collisions per second, right? So how are we supposed to process 1 billion collisions per second if we can only process 1 billion operations per second? Anyone know how big an event is at the LHC? How much data? If you wanted to store an event on tape, and record it to disk, so you can analyze it offline. How big is that? How many bytes? Any sense? 100 megabytes. It's not quite that big. That's not per event, but roughly megabyte scale is typical for an event, right? So remember, when they record the events, they're not just telling you the 4 vectors of the particles. It's not like a Pythia output, right? It really tells you from the electronics how much energy is recorded in each component and so on, and you have to add all of this up. So a typical event, event size is around 1 megabyte. Okay, but then you have a problem because you have you're having 1 billion megabytes produced per second. So clearly you can't save all of that to disk, right? You're limited by the capacity, the I/O capacity of your electronics, right? Roughly, you can write, the electronics allow around 200 megabytes per second to be written to tape, right? So that means you can record about 200 events to disk per second. Out of the 1 billion collisions per second, you're only allowed to save 200 to disk. Okay? So then you have a problem, and that problem is the problem of triggering. How do you decide which events to write and which events you don't want to write? And this is essential to understanding some aspects of the LHC, that they can't record everything. They have to choose what process they're interested in most. So basically, they have to go down from this gigahertz to this 200 hertz. So they have to do something, so they have to restrict. So, of course, if you only recorded Higgs bosons, you'd be fine, right? So one thing you could do is not record the event unless there's a very hard photon. If there's a photon with more than 50 GeV, you can save it, and everything else you throw out. And that would be fine, but then you might see this Higgs to gamma gamma, but you wouldn't see anything else. So the LHC is what's called the trigger table with a set of different kinds of processes that they're interested in and that they record to tape. So to give you an example of some of them, I should say, right. So for example, there's you might have one electron that's isolated with a PT greater than 25 GeV. So this is an example trigger at the LHC. Anytime you have an event, an isolated electron that's higher than 25 GeV recorded to tape, and this has a rate of around 40 hertz. So doing this alone, you have basically 1/5 of your recording capacity devoted to this channel. You could have one photon with PT greater than 60 GeV. This is also around 40 hertz. You could have one muon PT greater than 20, or 2 muons with PT greater than 10. And these are also 40 hertz. You might have one jet. Let me raise this up a little. PT greater than 400 GeV. Or 3 jets, PT greater than 165 GeV, or 4 jets greater than 110. This is all 25 hertz. And so on. There's missing energy triggers. There's a special Trowon trigger. And the idea is that you have to really put these hard cuts. Notice how hard this trigger is. So jets that have less than 400 GeV are just thrown out. We don't save those to disk because most of what QCD produces from you collide protons is jets. They're just hard. You have gluon scattering. You have gluons go out, and you produce jets. That's the dominant process that completely overwhelms everything else at the LHC. And so you have to put a very, very hard cut on the jets in order to not completely overwhelm your electronics. So these are our typical triggers. I should say there's sometimes we talk about level 0 triggers, which we call low level or hardware triggers. So these are things that are actually built into the electronics and that you can't really modify them. You can only change them when you shut down the LHC and get into the axis. So these are the lowest level, the first thing you do, which reduces, say, a gigahertz down to a megahertz. Right? So these are things like you can ask for electron, but you can't do something that involves, all of the detector. Because this is, remember, the electronics, this is a real machine, and the particles are going off in opposite directions, and it takes time to process and compare the particles that go in different directions. So you're limited by this gigahertz scale processing. So you can't just say, I want to look for, 4 jets. Because to know there's 4 jets, you need global information about the event. So that's not something that you can do. Even finding a jet, you have to use some kind of clustering algorithm and so on, and that takes time. So the first thing you have to do are these low-level triggers, which are hardware triggers, which just give you a rough pass that you want some hard particles that are hard enough that you keep the event. And those are the first triggers. And then we talk about level 1 or 2, which are software triggers. And those are often configurable and adjustable that let you change these things. And a lot of the triggers change as the luminosity goes up. At lower luminosity, you can get away with looser triggers, and at higher luminosity, you need to tighten the triggers. But this is important because it means if you have some beyond the standard model scenario that you want, that the signature of it is 200 GeV jets or even 600 GeV jets, you're just not going to see it. So the only things you can possibly see are the things that are written to disk. There's also things called prescales, which are, they take not all of the events that pass a certain cut. For example, you might take any jet that's greater than 100 GeV, but only take 1 in 1,000 of those events. So you save a little bit of it, which is helpful if you might have missed something and you just want to make sure that if you change your mind later on, you still have some information.
So what is a PT for 3 jets mean? Is it the sum of 3 jets?
No, it's each jet. Each jet has to be greater than 165. So you notice there's no 2-jet trigger? Why isn't there a 2-jet trigger? That's right. You're not just going to get 1 400 GeV jet. You're going to get 2, because when it goes off that way, there has to be something recoiling against it. So 3 is the next interesting case. This is just a sense, and these modify. These are just. I think I have a trigger table here in my.
What if you have a mono jet?
Right. So there's a missing energy trigger. Let me see where my trigger table is. Hold on. There. I lost it. Show you the video in a second. Okay. Stop it. There. Here's an example of a trigger table. These were low luminosity triggers when it's 10 to the 30, which is 10,000 times lower luminosity than it is. But this is an example of the kinds of triggers that Atlas and CMS. And they're slightly different, but they're roughly the same. So this missing energy trigger, if you're interested in monojets, this would be jets plus ET. In general, missing energy, to find missing energy, you have to add up the momentum of everything else and see what's missing, right? And that's a hard thing to do. So it's not something you can do quickly. It's a software trigger. And you can do it, but you do it later on. It has to be you have to make sure you didn't lose those events. You have to trigger something besides just missing energy, or you'll lose it. So large missing energy means you have large something else as well, which is often a muon or a jet or something else recoiling against. So these triggers are basically supersymmetry triggers designed to find missing energy, possible dark matter candidates,
So
and so on.
there is no universal trigger, but there is trigger search by search, basically.
No, the trigger. Well, the searches say, look, I'm looking. I know my supersymmetry model predicts this, so you better have a trigger so you don't throw this out. If you didn't know anything about model building and didn't have any reason to think there would be missing energy, you might not have put this trigger in. Okay. So it's motivated by particular theories and particular discovery signatures. The 2 photon signatures motivate a lot by things like Higgs boson decaying to 2 photons, right? And there's been some work, over the last 5-10 years, theorists have complained that they're not triggering on certain things. So, for example, something people have been interested in are displaced vertices. So you might have some new particle that's metastable and might decay after 40 centimeters in the detector. And if there's no trigger for that, you're not going to see it. So you say, well, we might just be missing this. New physics might be there hiding, and you have to go and then you have to jump up and down and get CMS to put a trigger so you don't throw that out. And there's people like Matt Strassler who do that professionally.
What's that eta parameter in the table?
Eta parameter. Oh, that's rapidity. So this is the cut. So they only look for central stuff. And I'll talk about rapidity and detector parameters. Go on. Yeah. I'm doing a horrible job repeating the questions.
Are these conditions united with and or proposition?
Or. The question was, are the triggers and or? And the answer is or. So any of these will trigger it. The ands are things like, when they're in this column, like 2 photons, that's an AND. Jets plus missing HE is an AND. But otherwise, each row is an OR. Yeah?
So we've calculated the average rates for random processes. What happens in the worst case scenario?
The LHC, the weasel blows up the LHC?
No, I mean, when there are many more events happening than expected. So how does the triggering and recording work?
Oh, how do they adjust the triggers when the luminosity goes up? Yeah, they're all luminosity dependent. So they have a whole set of tables if there's more collisions, they're not going to write all of they'll saturate the electronics and they'll have to loosen the triggers. So it's all set up to do that automatically. As the luminosity goes up, the triggers increase, and that's all continuous.
But my question was, even at a given luminosity,
Yeah.
these are the average rates, right? There are going to be times when these happen way more often than you expected on average, just statistically.
Right, but
So you have 10 times the events you expected just in that one.
I mean, well, there's a lot of collisions, so we're very close. The central limit theorem applies, and this is very Poisson distributions, and we kind of know what to expect. So there are deviations from the average. So sometimes instead of getting 200 events per second, you might get 190 or 210, right? So there's some flexibility there, but it's not. Or you might just throw out some, and probably when the electronic saturates, they just stop recording. I should say there is going to be a lecture by experimentalist Tom LeConte later on, so save your questions that I can't answer about things like offline luminosity, and he'll fill you in. This is just a jet plus anything else. It means inclusive over anything, so they don't require a jet plus another jet or jet plus electron. These are really out of date. They're very low luminosity triggers. Yeah.
Couldn't a 2-jet trigger be similar to a net trigger if they're not separated by a lot of pi? So you'd say you have 2 hard jets, but they're close to pi.
So the Met trigger would be much stronger. So you have 2 jets recoiling against a neutrino or something like that. I mean, maybe it could happen, right? Then that would set off the missing energy trigger rather than the dijet. If it doesn't satisfy the 1-jet inclusive trigger, it would satisfy the Met trigger. I don't think you get that. Okay. Okay, so that's where we're going. How do you... let me go back here. Okay, so let me show you, let's just see a little video of the LHC running. CERN has a number of these online, but it's fun to just see one to get organized. So they use Google Earth to zoom in on the LHC. Okay, so there's Lake Geneva. Geneva's over there. And there's that tunnel. So there's the main interaction points are Atlas and CMS, which are opposite sides. The thing starts with hydrogen, protons, hydrogen atoms, and they ionize them. I don't think it really comes out of a bottle, but I don't know. So they start by accelerating them linearly, and they send them into the proton synchrotron. That's the thing that broke a week ago, and they lost a week of luminosity. The proton synchrotron and this bigger one, the super proton synchrotron, are the injectors from a previous experiment at CERN that ran UA1, where they discovered the W and Z boson. Now they're used as injectors into the Large Hadron Collider. It's a nice thing about CERN is they build accelerators on top of old accelerators. So there's the big one. You see they have 2 beams, one going that way. These dots are the little bunches that I was talking about. These are the dipole magnets that are used to accelerate the beam. So again, these interaction points, this is Atlas. Okay, there's the artist rendition of a proton. Okay, that was there's an RF cavity used to accelerate and focus the beams. The 2 beams are next to each other in the pipe, and then they only cross at the beam line, at the interaction points at Atlas and CMS. Some of this is made by accelerator physicists. Maybe I should have picked one more about. You haven't seen this stuff. It's good to just see a video showing. It makes it a little more real. There's a lot that goes into it. That's the thing that collimates the beams towards the collision points. Beam wire scanner is something that's used to determine actually how many protons there are. It's a hard thing to measure. So these are luminosity monitors that tell you what the actual luminosity is. They also tell you the shape of the beam. you'd like it to be roughly Gaussian. So there's a picture of what the beams actually look like. They have to monitor these things so they can adjust them. And here they are recording the, I guess those are the triggers, so you have a lot of data come in and not that much go out. Here's it's all stored. So the data is stored. They store one copy of all the data at CERN, and the rest are distributed around the world to what are called Tier 1 centers. There's a Tier 1 center at Brookhaven, where Sally works. There's one at Fermi Lab for CMS. And then they're distributed from the Tier 1 centers. The data gets sent off to Tier 2 centers, where the processing is done. And then Tier 3 are people's home computers. Found the Higgs. Okay, enough of this. So what's next? So here's the trigger table. Yeah, let me talk a little bit about ATLAS and CMS, the basic layout of these experiments, the kinds of things they can measure. The design of the experiments are basically the same, and I'm not going to get into too much detail. I'll let the experimentalists do that later. From a theorist perspective, what you should know roughly is that there's this inner detector, which is designed for tracking. So that measures charged particles. It tries to determine their momentum. It helps you distinguish interactions that were from the primary thing that you wanted, the hard interaction, from pile-up collisions. ATLAS has a 3-stage inner tracker that has these silicon pixels right in the middle, which have the highest resolution. Then there's the silicon tracker outside of it, and then a transition radiation tracker. Outside of the tracking system is the electromagnetic calorimeter. In ATLAS, that's this orange thing here. So electromagnetic calorimeter is designed to tell if there are electrons or photons and measure the energy. So if an electron or photon comes through, almost all of its energy is deposited in this liquid argon calorimeter. So it basically excites the argon and forces scintillation, and you measure the energy there. Protons and neutrons, they're very heavy, so they get through the liquid argon calorimeter into the tile calorimeter. This is the Hadronic Calorimeter. At ATLAS, it's blocks of iron interspaced with plastic scintillators. So the iron causes showers, and then the scintillator measures the energy of those showers. And then the outside, so that's all in here. And then the rest of ATLAS, why it's so big, is for muons. So all of these big blue plates are to measure the muons. Muons interact very weakly, and they'll usually escape the detector before they even decay. So you want to measure their energy as well as possible. So you can only do that if you see the track bend, and you measure the curvature of the tracks. You need very powerful magnets. ATLAS has a 2 Tesla magnet. CMS's magnet is even stronger. It's 4 Tesla. Here's CMS. It's the same design. It's compact, although it's still enormous, as you can see from this person. It's the same basic idea. An inner detector with tracking system. They have, where is this labeled? So they have this, there's the electromagnetic calorimeter and the hadronic calorimeter. Their electromagnetic calorimeter is lead tungstate instead of liquid argon. Their hadronic calorimeter has brass plates instead of iron. But basically they're the same. CMS was designed to have a little bit better electromagnetic sensitivity through their slightly better ecal. ATLAS was designed to have slightly better angular granularity. I think in practice they ended up being about the same when they're running. So you don't really, as a theorist, you don't need to know too many of the details about it. One thing that's worth keeping in mind is the tracker has very good spatial and spatial resolution. Doesn't measure energy so much, but can determine tracks very precisely. The electromagnetic calorimeter also has better spatial resolution than the hadronic calorimeter by a factor of 3 to 10. And then the muon, well, I don't know what to tell you about the muon system. So you should roughly have a sense of the kinds of things we see. Almost everything that shows up in the detector is one of these things, either a photon, electron, muon, pions, or neutrons. And out of this, they're almost all pions. Something like 90% of the particles produced at the LHC are pions, which are either pi plus or pi zero. Why is pi zero not listed here? What does it decay to? 2 photons. Yeah, pi zero decays almost instantly to photons. So that shows up in the top line. So this just roughly shows you what happens to each type of thing. So electrons, you see, make a track because they're charged, and then they deposit all their energy in the ecal. Muons make a track. They deposit a little bit of their energy in the ecal, a little bit of their energy in the hcal, a little bit of their energy in the muon, and then get out. Right? Pions, you see them because they're charged. You see it a little bit on the ecal, and then they deposit the rest of their energy in the hcal. Neutrons are not charged, so you don't see them. They don't interact electromagnetically. You only interact hadronically, so they show up in the hcal. So these different components are relevant for understanding which kinds of things you can see and where they show up. What's next? So here's an example event display. You should get used to looking at these things because they're interesting, and I think if we ever see anything at the LHC, it's exciting. You want to know how to interpret them. This is an Atlas event. So the beam comes in here, scatters there. The tracks indicate what we know about the event. This is the E-cal that shows the energy deposits in the electromagnetic calorimeter, and the red is the H-cal, and the muons are on the outside. This is an azimuthal thing where you just project everything in this way. You can see it's essentially radial event. This is this is what's called a Lego plot, where each box, the height of the peak of the histogram, it's a 2D histogram, tells you how much energy was deposited in that area. I don't know. Maybe I'll show some more of these if they become relevant. So here's an example dijet event at the LHC, and these are just very energetic event. Okay. So let me leave that there for now. Okay. Are there questions so far about anything we've been discussing? Yeah.
Well, the LHC can detect pi as pi zero. I thought they would still detect it as a jet, but it would have photons in it. Like instead of pi zero, they can't detect it.
Well, they can see the photons, so they look like photons. Well, there's ways to. So what I was saying is the pion decays before it enters the machine, as does anything else. W also decays before it gets the machine. So there are ways to determine whether there was a pi zero there, or a W, or a B hadron, or anything else. There's methods to do that. But the things that are actually seen from the experimental point of view are all photons, pions, neutrons, protons, electrons, muons. Yeah. Oh, all of it. So heavy ion collisions, both CMS and Atlas record heavy ion collisions. When they collide after near the end of the run, they start colliding lead atoms, and they record data, and they have whole heavy ion teams.
Same magnet.
Yeah. Same magnet, same detector. They look for the same stuff. Because again, they're all just seeing pions and electrons and protons and photons. No matter if you collide lead or you collide protons, you have the same final state. They're just all the particles whose lifetime is longer than a nanosecond. Other questions?
Kaons also going to decay before?
Yeah, so kaons are kind of marginal, but often they decay before they show up. I mean, their lifetime is marginal, but sometimes they show up, or they'll show up as pions or muons or something. Okay, so now let's start talking about the kinds of things that you can measure at a Hadron Collider. I'll go start with this board. Okay, so the LHC collides two protons with momenta P1, basically 6.5 TeV. So it's going this way. The proton momenta is essentially light-like. The mass of the proton is clearly negligible compared to the 6.5 TeV energy. And this proton has P2 mu, has the same energy, 0.5 TeV. But it has a z component in the opposite direction. Conventionally, we take z to be this direction, z here, and then x and y are in the transverse plane. So what happens when you collide protons is, according to the Proton model, what we're actually colliding are quarks or gluons within the proton. So the proton has this momentum, but the momentum of... I'll draw this very conveniently. Try using a colored chalk. So we might have... say quark and an antiquark collide from within the proton. This quark is not going to have all of the momentum of the proton. It has some fraction. Of course, the quark is still going in the same direction as the proton, and the antiquark is going in the same direction as the proton, but the energy is smaller. So we write P1 for the parton momentum is x1 P1. Okay, you can't tell the difference in my P's. Let me write a Q. So the parton momentum I'm going to write as Q1 mu is x1 times P1 mu, and Q2 mu P2 mu. So these x's are the fraction of the proton's energy carried by the parton. So these don't have to be the same at all, right? This x might be 0.1 and this x might be 10 to the minus 3, right? So that even though these protons are back to back in the lab frame, in the frame of the partons, this one with a tenth of the proton's energy might be much more energetic than this, which has 1,000th of the proton's energy. So when that happens, the whole thing ends up going off in that direction, right? So from the lab frame, the protons just collide head on, but the partons are colliding where this one might be much more energetic than that one. So when you have these partons collide, it might look like that, and then the products go off. Let me draw this right. So we have partons come in, but then because the whole thing has a net energy going in this direction, because this one had a lot more momentum than that, the whole thing goes off to the side, right? So generally, collisions are not central. And I don't know if we can see that in this plot. This one looks kind of back to back. The more energetic they are, the more likely they are to be central.
So there's a saying like draw in or over the
So that's related to the parton distribution functions in the proton. We'll get into that in a minute. But so suppose, for example, you're interested in producing a W boson that decays to two jets, right? One thing you might look at is, say, the angle between the jets. Right? If the proton decays to quarks and the quarks turn to jets or leptons or something like that, you might be interested in how far apart they are. It's some characterization of maybe whether this was a W boson at all. But unfortunately, how far apart they are depends on what the energy was of the original quark that you picked, not the W boson. So you'd like to have observables that depend only on the W boson. In particular, you'd like them to be independent of whether this overall scattering event had a large momentum, longitudinal momentum, in the z direction. That is, you want to be independent of the boost in the z direction. You want to be invariant under taking the whole thing and doing a Lorentz boost this way or a Lorentz boost that way. So the kinds of observables we're interested in most are things that are independent of that. So the obvious thing is the transverse momentum, which is a vector, which we write as px, py. So it's a 2 vector, which just tells you the components of the momentum that are transverse to the beam. This is invariant under a boost that just shifts the z component and the energy. Another thing that's invariant is we can construct from this things like the Azimuthal angle, which is the angle between, say, x and y along the rotation of the beam. So if the detector is this big cylinder, we talk about phi, the azimuthal angle, as the angle around the cylinder, and we talk about a polar angle, theta, which is the angle along the beam. So you can think of this as the North Pole, and this is the South Pole, and this is the latitude, and then this is the longitude, or the other way around. I was getting mixed up. In any case, the phi is invariant under a boost, but theta is not. So theta is not a very good variable for measuring and characterizing things at a Hadron Collider. So how do we come up with boost invariant observables? Well, to do that, we need to know how a boost acts. We're doing it in time. Okay, I think I should be able to get through this. So what does a Lorentz boost look like? So a boost by an angle beta in the z direction acts you might remember this from representations of the Lorentz group. So that means that my momentum Q goes to boost acting on Q. So in particular, if I say Q mu had energy E and Qx, Qy, Qz, then E goes to E. Let me just abbreviate this C, this S. So E goes to EC plus QZS. Qx goes to Qx. Qy goes to Qy. Qz goes to QZC plus ES. Right, so the transverse components are boost invariant, and the energy and the longitudinal momentum mix under a boost. So because of that, I can now calculate what happens to this. This didn't work. Now if I look at this quantity, E plus QZ minus QZ, it goes to E times C plus S plus QZ C plus S divided by okay, and now let me multiply the top and the bottom of this by C plus S, and I get times, hope you can read that. So you get that this quantity shifts to itself times this factor, right? So the quantity is not quite invariant, but it rescales by something that depends on the boost. Okay? So you get a rescaling factor. So in particular, if I took the logarithm of this, it would shift under a boost. And if I took the logarithm of this for one particle and the logarithm of this for another particle, the difference between them wouldn't change at all, because each one shifts by the same amount. Right? So that motivates defining rapidity one half of the logarithm of E plus QZ. Right. So under a shift, this goes to Y plus logarithm of C plus S, and therefore y1 minus y2 goes to y1 minus y2. That is, differences in rapidity are okay, so differences in rapidity of boost invariant. The rapidity itself is not boost invariant, it shifts under a boost, but if you take the difference in rapidity between two particles, it'll be independent of how much relative energy the two partons had that collided. Okay, to get some intuition for rapidity, let's consider the example of
that's true for any any track.
It's just a definition. So any form momentum, you can construct the rapidity from the form momentum. Right? And then the question is, what are you going to do with it? And I'm saying if you take it from one particle and take the difference in another, it'll be independent of the rest frame. So to get intuition for it, let's take a massless particle. We're doing 5 minutes. Okay. Has E is the magnitude of momentum. Right? So if we draw a little triangle, so it goes off in this direction. So we have the scattering angle theta, the longitudinal momentum, the transverse momentum, and the magnitude P, which is the energy. And so cosine theta is Pz over the magnitude of P. which is dz over E. And so Y becomes 1/2 logarithm of so E, let's see, where were we? So PC is E cosine theta. So the E's cancel and we get 1 plus cosine theta over 1 minus cosine theta. We can simplify this using trig identities. This is 2 cosine squared theta over 2 divided by 2 sine squared theta over 2. The 2's cancel. And the log of something squared, I cancel the half. So this is just the logarithm of the cotangent of theta over 2. All right. So we define eta is defined as the log of the cotangent of theta over 2. And what we've shown is that eta equals y for massless particles. Okay, so there's two concepts, rapidity and pseudo-rapidity. Rapidity. So pseudo-rapidity is geometric. Pseudo-rapidity is just a function of the angle. But for a massless particle, it happens to be equal to rapidity. Rapidity is a kinematical quantity. It depends on the energy, it depends on the form momenta of the particle. Okay? So pseudo-rapidity is nicer from an experimental point of view, because if I tell you where a particle went, you know it's pseudo-rapidity. Rapidity is nicer from a theory point of view, because it tells you about, it depends on the momentum, it's a thing that's formally boost invariant. For massive particles, rapidity is not, pseudo-rapidity, differences in pseudo-rapidity are not boost invariant. For massless particles, they are, because it reduces to rapidity. In general, most particles of the LHC are essentially massless to first approximation, except for jets. Jets, if you think of a jet not as each particle in the jet, but as a collection of particles, it can have a significant mass. Also, things like top quarks can have significant mass, or the Higgs boson. So if you're trying to reconstruct those objects, not their decay products, then you have to be careful about the difference between rapidity and pseudo-rapidity. But that's basically how it works. Just to give you a sense of it, so pseudo-rapidity, so theta pi over 2, so that's, here's my beam. So that's central. This corresponds to eta equals 0. So eta equals 0 is right between the beams, right in the central region. So when we had those numbers like eta of 2.5, so eta of 2.5 is corresponds to theta of around 10 degrees. So that's over here. So this is so eta. Let me write eta less than 2.5, the absolute value of eta. So eta is negative over here and positive over here. So the region of eta between minus 2.5 and 2.5 is essentially the central region down to around 10 degrees from the beam line. That's the region where most of the detectors are most sensitive. So in this picture, it goes pretty far. It's I can't really reach. But over here is around eta is 2.5. So the atlas has a break at around 1.8, and then it goes down to 2.7 or so, which is around there. The CMS is similar. So it goes down. So it has actually pretty good coverage, almost 4 pi coverage. Okay, so that's I think a good place to stop. So next time we'll talk more about observables and kinematics and get towards the standard model. Yeah. Yeah, sure.
Oh. That's probably the event.
Maybe other people want to ask questions.
I mean, as you like. Well, let me see if people have questions about the lecture. Hi. He was asking me something else, totally irrelevant.
Okay. Well, I have actually three very basic questions. One of them is like when you were showing the table of the triggers, for like all of them are 2.8 out of 2.5.
Yeah.
But then MET was 4.9, and is that because how MET is reconstructed is because like just trying to?
Well, MET itself doesn't have a rapidity. Let me see what.
So that one I thought it was like for the kind of like the full.
Let me see what that means. This 4.9. Yeah,
something's like 3.2, like that.
Yeah, so that means so good. So this the MET 4.9 means that they include all the particles. So when you start,
soft stuff.
yeah, they include everything that they see down to rapidity of 4.9. That's basically the entire region that the detector covers. So that includes the forward region, because if you really want to get ET right, you have to measure all this stuff. You have to measure everything, right? ET is a very, very hard thing to measure, and there's huge uncertainty under it. It's one of the biggest challenges of the LHC is understanding the uncertainty on it. So they take it. That's why the accelerator has to be so big, so they can measure stuff.